Okay. All right. So if you'll take a look at the notes there, this is what this chapter is on. The whole thing's on sequences and series. And what we're going to do today is we're just going to kind of familiarize. Hello. Thank you very much. We're just going to kind of familiarize ourselves with some of the notation, some of the vocabulary that we use for these, and then kind of get used to them a little bit. We do end up with some kind of interesting formulas here. They are in the textbook. You don't have to use every single one of them, but the more you familiarize yourself over the weekend with 9.1, how it works, how we write these out and stuff like that, the better off you're going to be in 9.2 and 9.3, because in 9.2 we deal with a very specific type of sequence and series. It's called an arithmetic sequence. And then in 9.3 we do geometric sequences. Okay, they come up quite a bit. Both of those do. So they're good things to be aware of, especially if you're going to go on in math. So let's take a look here. So it starts off, it says, a sequence is a blank of numbers usually produced by a formula. Okay, all a sequence is it's just a list of numbers. So we're just going to list out a whole bunch of numbers, and some of them are going to look very familiar, especially the first one. Now the book describes a sequence this way. It says a sequence is a function whose domain is the set of positive integers. So it's a list of numbers that's produced by a formula or a function, as the book says, but the only type of numbers that we can plug in are positive integers. So we usually start by plugging in a 1, then we plug in a 2, then we plug in a 3. Plugging in a 1 produces the first term, plugging in a 2 produces the second term, 3 produces the third term, and so forth. Okay? So each individual entry, or each individual entry in the list of numbers, is called a term. And each term has a counter. And that counter has a technical name. It's called an index. Okay? But you can think of it like a counter, like I was describing. The 1 says it's the first term, 2 says it's the first term, second term, and so forth. Okay? So we're going to go through several examples. The first one's really easy, and then they get a little bit more difficult. In fact, we introduce some notation. This notation right here might look a little bit weird. Maybe you've seen that before. If you have, great. If you haven't, I'll explain where it comes from. Okay? So you'll notice that each one of these, at least the first 4 or so, I've used a different letter to indicate what sequence this is. So this is the sequence A. And the way we read this is A sub n equals n. Okay, now this is the index. And the index goes in 2 places. And I need you to listen to this very carefully. The index goes right here. It's the subscript. It tells you what term you're on. And it gets plugged into the formula that produces the terms. Okay, so this is called an nth term formula, or a general formula, and we're going to write this in what we call expanded form. So this is like a little compact formula that you can just write down. Hey, here's the whole sequence just in one general formula. And then if we're going to go through and we're going to actually write out what this sequence looks like, here's what we do. I'm going to write an a sub 1 for the first term, a sub 2 for the second term, and so forth. So this is going to be a sub 3, a sub 4, a sub 5. And the instructions on this said that they wanted us to write down the first 5 terms. So a lot of times it's really helpful to go ahead and write down the little subscripts, because that reminds me, well, if I plug a 1 in right here as the subscript, so if I turn that into a 1, I need to turn that into a 1. So whatever the index is, I put that right here. So if I put a 1 here, I'll put a 1 here. The first term is a 1. It's that simple. If I'm doing a sub 2, if I'm on the second term, I put a 2 right here and I put a 2 right here. So the second term is 2. Third term is 3. Fourth term is 4. Fifth term is 5. So if you'll notice this formula right here, it's a very simple formula. Whatever the index is, that's the term we're on. So if I wanted to know the 97th term, the 97th term is 97, okay? So these general formulas are really pretty cool, because you can just plug in the index right here and right here. Right here it tells you what term you're on. Right here it tells you the value of the term. So let's take a look at this one right here. I'm going to change colors for this. So I need to produce b sub 1, b sub 2, b sub 3, b sub 4. We normally put commas in between each one of these, okay? So I'm going to put them up here, because that's where my list is going to be. B sub 1 is what I get when I plug in a 1 right here. So it goes in the index and it goes in this place in the formula. So this is going to be 2 times 1. So what's the first term? 2. All I have to do now is come back here and I replace the index with the next in line. So that's going to be a 2. Put a 2 here. What's the number? It's going to be a 4. Okay? Hang on 1 second. Good, we're still going. Okay? So what's the third one? 6, 8, 10. Now, if I asked what the 100th term was, 200. Okay, it's that simple. Okay, are there any questions there? Okay, let's take a look at the next one. The next one gets a little bit interesting because there's more than one place where I need to put the index. Okay, the index goes here for the first term, so I'm going to write C sub 1, C sub 2, C sub 3, C sub 4, C sub 5. Again, when I say C sub 5, that just is a fancy way of saying, a mathematically precise way of saying, that's the 5th term. Okay? So if I'm going to do C sub 1, if I'm going to find the first term, that's what this means. Then I'd plug in a 1 right here and a 1 right there. And then I'd calculate what that is. It's negative 1 to the first divided by 1. So what is the first term? Negative 1. Put a comma. Let's figure out what the second one is. So again, where I'm going to change the index, I'm going to change the n right here. So second term, negative 1 to the second divided by 2. Positive 1 on the top, 2 on the bottom, so the second term is 1/2. Put a comma. Let's do the same thing. Now, the more complicated the formula, the more terms we have to write down before we can spot a pattern, because there's usually a pattern to all of these. That's why we can write a little compact formula for this. So that's going to be a 3 in all 3 of those places, the index and the 2 places where the index appears in the formula. And what is it? Negative 1/3. Now, is there enough of a pattern here that we can predict what C sub 4 is, what the 4th term is in the sequence, without actually plugging it in? Okay, it's going to be positive, right? And it's going to be 1/4. Now, if we just double check that, let's just check and make sure. 4th term would be negative 1 to the 4th over 4. 4 negative ones gives me a positive 1 on top, 4 on the bottom. There we go. What's the 5th one going to be? Negative 1/5. Any questions? Okay, raise your hand if you've seen this notation right here on D. A couple of you? Okay. Sarah, what's it called? Do you remember? Factorial. It is. Very good. Okay. It's called a factorial. A factorial is a fancy way of, or a very short, compact way of writing a very long multiplication problem. Okay? Just like if we learn how to do, like 2 to the 8th would be 2 times 2. We write out 8 2's all together. This is a short way of writing. If I write 5 with an exclamation mark behind it, it said 5 factorial. It's not a really excited 5. What it means is you take that number that it started with, 5, and you multiply it by every positive integer below that. So that's going to be 4 and 3 and 2 and 1. So if I multiply those together, that's what 5 factorial would be. I'm going to work backwards here for just a second. Okay? 1 factorial is just a 1. 2 factorial is 2 times 1, so that's a 2. 3 factorial is 3 times 2 times 1, so that's a 6. 4 factorial, 4 times 3 times 2 times 1. Can you see how to go from one term to the next term? 3 factorial is like 2 factorial times 3, isn't it? There's the 2 times 1 right here and right here. Times it by 3. So we're going to times this by 4. So this is going to be 24. So I'm going to times 24 by 5, and that's going to give me 120. Okay? So 5 factorial is 120. 4 factorial is 24. 3 factorial is 6, and so forth. Okay? These numbers get really big really quickly. What if I wrote 6 factorial? Okay, it's going to be 6 times 120, or another way to write it would be 6 times 5 factorial, 6 times the factorial that was below it. So if you know the one below it, this is going to be 6 times 120, which is 720. Those numbers get really big really quickly. Okay, factorials grow very, very, very fast. Okay? Any questions? Does anybody know what 0 factorial is? Okay, it is 1. Okay? Now we could go into a proof why that is. Let me give you just a little hokey argument. Notice there's a 1 in every one of these. Okay? If you add a 1 to any multiplication problem, it's not going to change what the answer is. Okay? So there's no other number there other than a 1. Okay? If you're interested in going through a proof on why that is, I'll show you one after class. Yeah. Are there any positive integers less than that? No. Stops at 1. Yep, we'll talk after class. Okay, so let's take a look at this. If I do d sub n is n factorial, so this is going to be the first term, the second term, the third term, the fourth term, the fifth term. This is going to be 1 factorial, 2 factorial, 3 factorial, 4 factorial, and 5 factorial. Okay? Now, I could leave it like that, but we'd probably like the list that it represents. So that's going to, again, be 1, 2, 6, 24, and 120. There is our sequence. Sequence produced by that formula right there. Okay, would you do the next one? Would you go ahead and write out what a sub n is here? So do E. First term's a third, right?
Yes.
2 on the top, 2 plus 2 on the bottom, 2 over 4. Now, I could reduce that, but let me show you why you wouldn't want to reduce that. The third term is going to be 3 over 5. The fourth term is going to be 4 over 6. Again, I could reduce that, but it's pretty easy to produce these terms if you notice the pattern. What's happening to the top? 1 bigger every single time. In fact, it's the same as the index. So if the index is 5, the top's going to be a 5. And what about the bottom? Okay, it's 1 bigger every time, so this is going to be a 7, or a better way to look at it as, look at the formula. The top is n, the bottom is n plus 2, or in other words, it's 2 bigger than the top. So this is going to be a 7. And again, the cool thing about this is we could actually figure out what the 102nd term is. The 102nd term is 102 over 104. It's that quick once you spot the pattern. Any questions there? Okay, now there's not a lot of cleanup that you could do on this one. Okay, there's not any simplification or anything. So the first term is going to be a 1 over e to the first. The second term is going to be 2 over e to the second, 3 over e to the third, 4 over e to the fourth, and so forth. Okay? Now you have several problems where all they're doing is they're just getting you to write down the first 5 terms, just getting used to how to work with these formulas, how to produce a little sequence there. So writing it down from the general formula to the sequence is a piece of cake. What if we wanted to go backwards? What if we wanted to take a sequence and write a formula for it, write an nth term formula for it, a general formula for it? So let's take a look at this one right here. Okay. Again, let me make sure everybody caught that. This is called an nth term formula. Okay. So we could call it a general formula or an nth term formula. And what can be really helpful with this is doing the exact opposite of what we just did. I'm going to write a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. That way I've written the term underneath each one of them. And what I want to do is I want to see, can I find a relationship between the index, the term that I'm on, and how to produce these numbers. So if I plug in a 1, I need to get a 1 over a 2. If I plug in a 2, I need to get a 2 over a 3. Plug in a 3, I need to get a 3 over a 4. And my goal is, can I come up with some little formula that would produce any one of those I want? going to be a fraction, right? What's the top? It's going to be n. What's the bottom? 1 bigger than n, so that's going to be n plus 1. Again, it's just spotting the pattern there. Okay, are there any questions? Let's take a look at the next one. I'll do b sub 1, b sub 2. If you wanted to do a every single time, that would be fine. It doesn't really matter. It's just nice to have those a little bit differentiated. So I'm going to write b sub n equals, going to be, yeah.
Well, I have a question.
What?
So there's multiple answers, like on this a, it could be n minus 1 over n.
Sure. Okay. So John points this out. He thought about it this way. He said, you know what? I'm going to do this. I'm going to do, what did you say? N minus 1 over n. Okay. Does that work if you plug in a 1? No. Okay. So usually so when we get to the series, you're going to have a choice about how to write it. But if you're going to start with a 1, you've got to make it this one right here. Does John's work? If you start by plugging in a 2. Okay. So your idea is good, but if we're going to start with 1, if we're going to use all the positive integers, this has got to be it right here. Okay. Got to be a fraction. Ooh, not even that. Top's a 1, bottom is a 3n, right? Does that work? Okay. Let's take a look at the next one. Okay, Sarah, what did you say?
N over the quantity n plus 1 times the quantity n plus 2.
Wow. This is kind of a combination of the formulas that we've worked with a little bit earlier. That one up above, let me make this a little bit smaller, kind of like this one right here, and a little bit like this one right here. Let's take a look at the relationship that we've got going here. If we look at the top, it's 1, then it's 2, then it's 3, then it's 4. It's exactly the same as the index. And again, if you have to write this down, let me change to that C, C2, C3, C4, C5. If you have to write that next to it to spot the pattern, go ahead and do that. So the top is the same as the index. The bottom is 2 different factors, a 2 and a 3. Or in other words, the first factor is 1 more than the top. The second factor is 2 more than the top. That's why we've got n plus 1 over n plus 2. Are there any questions about that? Okay, whoops. So let's look at the next part then. It says if you were given any of the formulas above and were asked to find the 102nd term, it would be pretty easy. So even with something like this, what's the 102nd term of this one? 101st. 101 over 103, right? Okay, so pretty darn easy. Okay, now, that's called an nth term formula or a general formula, and they're really useful, but there is another type of formula that's also useful. It's called a recursively defined sequence. A recursively defined sequence. And a recursively defined sequence uses previous terms to define the terms that follow. So uses previous terms to define the terms that follow. So in other words, the new terms are defined in terms of the old ones. So you can't figure out the new ones unless you have the old ones, okay? And because of that, you've got to have 2 things in order to have a recursively defined sequence, okay? A first term, or terms, sometimes they'll need more than one, and a formula to get you from the terms you have to the terms you want to find. So from the terms you know to the next term, or terms, as the case may be. So this is the first one that we're dealing with that's a recursively defined sequence. Make that a little bit bigger. And let's take a look at this one. Okay? So this is a little bit weird. This one gives you the first term right here. And then the formula for the other terms isn't like our nth term formula. You'll notice what we've got here. This still has an a sub n. It's got a place for you to put the index. And then over here it says a sub n minus 1. Well, the way to think of this is this. This is the next term. And this one right here. So if I'm on a sub 1, or sorry, let's do a sub 7. this would be 4 times a sub, well, let's see. If there's an n here, I put an n there. What did I put right here? A 7. 7 minus 1. So that would be 4 times a sub 6. So this is the next term. This is the term before it. Or I'll just put term before. So if you're on the nth term right here, and this is the n minus 1 term, that's the nth term, that's the one right before it. Again, notation might seem a little bit weird, but it's something that you've got to get used to if you're going to be good at these next 3 sections. Okay? So again, I'd encourage you to write down a sub 1, a sub 2, a sub 3, and so forth. So we're going to write down a sub 1. A sub 1 is 3. I'm going to circle that. I know that's a sub 1. They gave it to us. They gave us a starting point. Now I want to find a sub 2. So put a 2 right here and put a 2 right here. So this is 4 times a sub 2 minus 1. Or if we wrote this subscript the right way, there's a little bit of arithmetic to do here. It's 4 times a sub 1. So to get the second term, everybody watch please. To get the second term, you take 4 times the one before it. That's 4 times 3, so that's 12. Does that make sense? That's a sub 2. So to get to the next term, you just do 4 times the one before it. To get to the second term, you do 4 times the first term. Let me say this again. Look right here. To get to the next term, you do 4 times the one before it. So if I want the third term, I'll do the arithmetic here one more time. A sub 3 minus 1, that's 4 times a sub 2. So again, the third one is 4 times the second term. That's going to be 4 times 12. So what's the next one? 48. Now, is that enough that we can just write down what the fourth term is? 4 times the third term, right? What's 4 times 48? 192. 192 is the fourth term. And the fifth term would be 4 times the fourth term. So I'm going to do 4 times that. So that's going to give me, what do we say? 768. Okay? So there is the first term, the second term, the third term, the fourth term, and the fifth term. Okay? And again, that's called a recursively defined sequence. It's a formula that allows you to figure out the terms that follow written in terms of the ones that were before it. Okay? So if you flip the page over, this says list the first 7 terms given by, now, a sub 1 is 1, a sub 2 is also 1, and then it's got this formula right here. This is the term we want. What is this term right here? So this is the next term. What's this one? The one right before it, and what's this one? The term 2 before it. Okay? So this is the term that we're on. This one's the one right before it, and this one's the one 2 before it. So a sub 1 is 1. A sub 2 is also 1. I want to find a sub 3. A sub 3 is going to be a sub 3 minus 1. That's 2. Plus a sub 3 minus 2. That's a sub 1. So in order to get the third term, what do? Yeah, add the previous 2. Okay? So that means the third term is 2. If I want the fourth one, this notation means I need the one right before it. If this is the nth term, this is the n minus 1 term. So that's going to be the third term. If that's the nth term, this is the n minus 2 term. So that's going to be the second term. You with me there? Got it? So this is going to be, well, let's see. The third term was 2. This one was 1. So altogether that's 3. Now, what's the fifth term? Fifth term is going to be 5. Have we spotted the pattern? Take these 2, add them together, you get 2. Take these 2, add them together, you get 3. Take these 2, add them together, you get 5. Sixth term, 8, 7th term, 13. Does anybody recognize that? It's the Fibonacci sequence. Okay? Comes up a lot in nature. There's some really cool places. Let's see. A couple of them would be if you get a pineapple. You ever noticed how you can look at a pineapple and there are spirals on the pineapple that go this way? And if you look at them the other way, they go this way. So it's kind of spirals around this way, okay, and then spirals around this way, clockwise and counterclockwise. If you count the spirals going clockwise, they will be, I think they're usually 8 and 13, okay? Clockwise is 8, counterclockwise is 13, or vice versa, however it works out, okay? There are lots of things that work out that way. Okay, any questions? What type of definition is this? Recursive. Okay, it's not an nth term formula. It's not a general formula. Those are really nice. Okay. Recursive definitions have their uses. There are some times where they're really useful. Okay. A lot of times they're a pain in the butt. Like if I said this. What if I said find the 102nd term of that one? Yeah, because you'd have to get, what terms do you need? The 100 and the 99th, right? And to get the 100 and the 99th, you need the 98th, the 97th, and all the way back. You have to make the list in order to produce it. Okay? Any questions?
Yeah.
What?
Is there an easy way to do that, like in like a calculator or something?
Not on the calculators you can use. No.
Oh,
No.
that's why they banned them.
There you go. Now remember, they banned them because people just like punching buttons. Sometimes teachers teach punching buttons, and sometimes students just like punching buttons and not learn how to do it. Okay, so let's move on to the second part of the section, or the second idea that we need to cover in this chapter, and that's something called a series. So a sequence is just a list of numbers. It's got commas in between. A series is a list of numbers that's been added together, or we say that it's been summed. We've added these up. So we're going to write out these sums using the Greek letter sigma. So this right here is the Greek letter sigma. It's a Greek letter S. It stands for sum. Okay? So you'll notice that what we've got here is what looks a little bit like a formula for a sequence, except for we've changed the index now. So this is the index. The index is going to be K. It's going to start at 1 and it's going to stop at 5. And here's the formula that produces the terms. These are called a summand. Okay? So this is where the index starts, this is where it stops, and this is the formula that produces the terms that we're going to add. It's called a summand. Yeah?
Isn't the sigma what we use to find a function? Like we plugged it in.
What do you mean?
This one on one of our worksheets, you had to find the function, you had to go through the sigma sign.
Anybody else remember that?
No, I guess I learned it last year then.
Could have been. Either that or you're smoking crack.
That's it.
Okay.
It's marijuana and it's legal.
Oh, okay. Whoa, good one. Good one. Okay, so here's what we do. Again, if you have any trouble with this, you can write out what's the first term, what's the second term, what's the third term. Okay, in this case, I start out with a 1, and where do I stop? I stop when I get to the 5th term. So if I plug in a 1, the first term is a 2. Write a plus. Second term is a 4. Write a plus. 6, 8, and 10. Okay? So this is called right here, let me change colors here. This is called sigma notation. Okay? This right here where we've written it out, again, that's called expanded form. And if we figure out what it equals, if we add these up, like if I put these two together, that's a 10. If I put these two together, that's a 10, and that's a 10. So what's my sum? 30, okay? So that right there is called the sum, okay? So sigma notation, nice compact way of writing it. Expanded form, where we write the whole thing out, and then the sum is the answer to that, okay? Any questions? Okay. Where does this index start? Starts at 1. Doesn't always have to start at 1, but most of the time it does. Occasionally it'll start at 0, or there might be some good reason to start somewhere else. So we're going to start by plugging in a 1. So if I plug in a 1, let's write down the first term. This is going to be 3 minus 7, so that's going to be negative 4. Then I'm going to write a plus, plug in a 2. 6 minus 7, the next term is negative 1. Plus, we're now at 3. That's 9 minus 7, so that's a 2. Next one, 5. Next one, okay. Now we have to go we have to have 6 terms altogether. So if I plug in a 6, that's going to be 18 minus 7. The last one's going to be 11. So again, there's my expanded form. There's expanded form. And we want to figure out what the sum is. So I can cancel off these two guys make a 5, and that makes a 5. So those are gone. So I've got a 10. Altogether, I get a 21. There's the sum. Sigma notation, expanded form, there's the sum. Now, did anybody spot anything when we were writing these down so that you could write them down more quickly than going back and plugging in the index? One more. What is it?
Just plus 3.
Yeah, it goes up by 3 every single time. It starts at negative 4 and goes up by 3 every time. Any questions there? Okay. All right. Let's take a look at the next example then. Okay, this one says start at 1 and go till you get to n. Well, that's not very specific. Okay, this is what we call a finite series. It starts and stops at a certain place. So this one starts when you plug in a 1, starts at the first term and stops at the 5th term. Starts at the first term, stops at the 6th term. This one starts at the first term and it stops at the nth term, so here's how we write it. Well, when we plug in a 1, you get a 1/2. When you plug in a 2, you get a 2. When you plug in a 3, you get 9/2. When you plug in a 4, you get 16 over 2, so you get an 8. And again, it might be easier to write this. Oops. See the pattern there? Always 2's on the bottom, always perfect squares on the top, so the next one's going to be 25 over 2. Okay, then we just put plus dot dot dot, put a plus, and then we put the last term. Well, the last term is what we get when we plug in what? An n. So that's going to be an n squared over 2. And this right here is the answer. Okay, that right there's the answer. It's an expanded form. Now, I'm going to show you a little bit later. There are some times where we could actually come up with a nice nifty little formula for something like this. Okay? Any questions? Yeah.
How far, you know how we have 1/2, 2, 9/2?
Usually
Just
3 of these and then dot dot dot. If you wanted to, you could write the second to last one. It would be n minus 1 quantity squared over 2 because it's the one right before it. Okay? That's not a bad idea to get used to that as well. Okay? Couple at the beginning, 1 or 2 at the end. Any questions? Okay. All right, let's take a look at this next one. It says express the following sums using sigma notation. So on this, we're going to go from the expanded form to the compact form. So we're going to write sigma notation. Okay, I think this book uses K. You could use any letter you want for the index. I, J, K are usually pretty common ones. Okay. One thing that can be helpful is to write down the index next to whatever we're on. But we wouldn't be quite sure where we're going to stop there, but can you notice what the formula would be? What would the nth term formula be here? Okay, n or whatever I chose to use. In this case, I chose to use a k, so it's going to be whatever the index is. We're going to start by plugging in a 1, and we're going to stop when we get to 40. Okay? There it is right there. Next one. First term, second term, third term. Not quite sure what term that is. Let's come up with a formula and see if we can figure this out. Sigma notation. Again, I'm going to start with K. What's the relationship between the index and the term? Double it. So we're going to do 2K here What k do I start by plugging in? 1, right? If you plug in a 1, that would produce a 2. Plug in a 2, that would produce a 4. Where do I stop then? It would be 19. In other words, when does 2k equal 38? When k is equal to 19. When I'm on the 19th term, that's when I'm going to stop. So again, there's the sigma notation for that one. Any questions?
Yeah, I guess I do. Do
What?
they always start at 1 with those things?
We could adjust it a little bit. In fact, I'll show you on this one where we could adjust it. We could kind of use John's idea on this one. Okay? All right. So let's say this is the first one, the second one, the third one, and so forth. Not quite sure which one this is. I need to figure that out so I know where to stop. We're going to start at k equals, well, let's see. If I'm using a 1 here, let's start at 1. It's going to be a fraction. Remember how I told you could spot this before? How does the top relate to the term that we're on? First term tops a 1. Second term tops a 2. It's whatever the index is. So that's going to be k in this case. How does the bottom, how does the denominator relate to the index? It's always one more. So we're going to do k plus 1. Now, I wrote this in this specific way. Then it wouldn't be very difficult to figure out. When do we stop? 13th term. Okay. Any questions? Okay, watch. Let's say I wanted to start at k equals 2. If I wanted this to start at k equals 2, well, that would be like a 2 and a 3 and a 4 and so forth. So what's the bottom? The bottom is 2, 3, 4. So it's whatever k is. How is the top, don't say anything out loud, how's the top related to the bottom? Think about this. How's the bottom related to the top? We knew what to do here. How do we kind of do this in reverse? How's the top related to the bottom? It's 1 less. So this is going to be k minus 1. How far do I go then? From 2 all the way to, do we stop at 13? No, we have to stop at 14, because notice what happens when you plug in a 14. If you plug in a 14, the top is 13, the bottom is 14, just like we had there. So either one of those would be fine. Again, on the front page, when you're writing down a sequence, we start with 1 all the time. Usually we start with 1 if we're writing down a series, okay? But you can adjust that, you just get a different formula. So there are lots of different answers there. Okay, are there any questions? Okay. We're going to move through these next couple pretty quickly because these should be pretty easy. What is every one of these terms? Answer's 24, right? Because there are 4 6s. This is going to be -5 plus -5. How many -5s? 8. So the answer to this one is going to be 8 times -5. Started at 1, stopped at 8. That means there's going to be 8 of those numbers right there. So on this right here, what if it was that constant and we had n of them? What's the easiest way to find the answer? N times C, okay? So there's a little formula. If they're always constants, if they're the exact same one, all you have to do is know what the index is, especially if you start at 1. How many of those did you add up? Any questions? Okay, then the next one's kind of interesting. I want you to take a look at this. This is actually something that this is credited to, I think, let's see, Carl Friedrich Gauss, lived several hundred years ago. He was probably 8 years old when this happened. He was in a one-room schoolhouse. Teacher got angry at the students and said, hey, need you guys to shut up. Probably didn't say shut up back then. I want you to add up all the numbers from 1 to 1,000. Okay, so add up the first 1,000 positive integers. So what he wanted them to do was this. 1 plus 2 plus 3 plus 4 plus ... all the way to 998, to 999, and to 1,000. Wanted them to come up with an answer for that.
My teacher made us do this last
Right, so what did you do?
year. I did that.
Okay, What young Carl figured out was, this is going to be a pain, but watch what happens. There's a pretty cool pattern if I write the same one in reverse. So we need to find this answer right here. He goes through and he says, well, let's take 1,000 plus 999 plus 998 plus ... This would be 3, 2, and 1. What do these two add up to? 1,001. 1,001. 1,001. 1,001. Every one of these is 1,001, right? Now, if I add these up, these are all the same constant, just like these problems that I just got done doing over here. So, how many of them are there? 1,000 of them. And what number are they? They're 1,001. Now, what's the problem with finding the answer to this list right here? It's two of the original list. It's the same list written backwards. So there are two of them. So we divide that by 2. So this is going to be 500 times 1,001. And if I'm not mistaken, that's what it is. 500,500. Pretty cool, huh? So there's actually a formula, and it's in your textbook. I'll write it up here. If you're adding up the first n integers, you get n times n plus 1 divided by 2. So that's like having 1,000 up here. 1,000 times 1,001 divided by 2. Okay? Those are all in your book. I'll show them to you again in just a second. Okay? So the sum of the first n integers is n times n plus 1 divided by 2. So we can there are actually formulas, and you can use clever techniques like I just did to figure out what the sum of the first perfect squares are. So this would be, this would be like 1 squared, 2 squared, 3 squared, 4 squared, all the way up to 10 squared. And this would be 1 cubed, 2 cubed, 3 cubed, all the way up to 8 cubed. Now, you could figure out every one of those, or let's take a look at the formulas. Those three right there. Sum of the first n integers, n times n plus 1 divided by 2. Okay, if you want to sum up the first n perfect squares, it's n times n plus 1 times 2n plus 1, all divided by 6. That's pretty ugly. And if you want to do the first n cubes, it's n times n plus 1 divided by 2. All of that squared. Lots of practice. Okay? Now, the interesting part is, take a look at these cubes. Does any of that look familiar? It's the sum of the first n integers. It's this right here, squared. So really, it's not like memorizing 3 different formulas. It's really just 2. Okay? It's just that if we're going to cube them, we end up squaring them. Okay? Funny how that works out. Okay? We'll use those in just a second. I want you to take a look. Let's take a look at these two right here. This is called the sum and difference property for summations. If you've got 2 terms that are added together, you can find the sum of the first one and the sum of the second one and just add the answers together. Same thing with subtraction. Find the answer to the first one, find the answer to the second one, just subtract them. Okay? We won't worry about that one for the time being, but that one might be a good one to come back and take a look at. Okay? And this one says, if you've got an answer to this one right here, if you know what the sum is for this, if you multiply every one of the terms by a c, you can just pull that constant out front. Okay? So I'll show you how these work. So let's slide back up here. And let's take a look at this one right here. The formula for this is n times n plus 1 times 2n plus 1 divided by 6. And in this particular case, we're adding from 1 to 10. So what's n? What do we plug in here? We plug in a 10. Okay? So the answer to this problem is going to be a 10 times 11 times 21 divided by 6. I'll let you do the arithmetic on it. On this one, remember, it's n times n plus 1 over 2, and then we're going to take that whole thing and square it. So what's n on this problem? What's n on this problem? 8. So this is going to be 8 times 9 over 2 squared. So, I mean, it's not that bad to figure out from scratch. I'm going to cancel this with this. That's going to be a 2. That's going to be a 7. I'm then going to cancel the 2 with the 10. That's going to be a 5. So I've got 35. 35 times 11, 385, right? 385. On this one, I can cancel the 2 with the 8. That's going to be a 4. So I've got 36 squared. 36 squared, is that 1296? Okay. You might think, well, my gosh, I can just add up those 10 numbers, and I can just add up those 8 numbers. Please use the formulas, okay? Because it will get to a point where, what if this was 500? You don't want to write out all 500 of those and add them up, okay? Much easier to plug into the formula, so please get used to that. Okay, last 2 problems, and we're going to use the formulas for this. Okay, take a look at this one right here. This is a 3 times a c. So if I were to write it out, I get a 3. Whoops. Let's see. There's a typo here. This should be that should be a k. That should be a k. Thought that looked funny. Yep, that's a k. So that means the first term would be 3, 6, 9, ... all the way to 3n. We end on n. Okay. One way to figure this out would be pull the 3 out front, and we're going to sum from 1 to n of k. Isn't this the sum of the first n integers? Okay. Don't we have a formula for this right here? The formula would be n times n plus 1 divided by 2, right? What about the 3? If every one of those was 3 times bigger than it was, then our sum should be 3 times bigger than it is. And here's a formula that will add up the first n multiples of 3. Again, a little bit brain stretching here. You've got to think about, gosh, that formula worked. We showed that this formula produced n times n plus 1 divided by 2, that little Carl Friedrich Gauss thing, okay? Adding up the first 1,000 integers. We figured out that formula. Well, what happens if every one of those is multiplied by 3? The sum ought to be 3 times bigger than it was before. Okay, so let's take a look at this one right here. Okay, this one I'm going to use the sum property and that little constant multiple, and we're going to write it like this. I'm going to write it as a 2. Let me change colors so we can keep these straight. I'm going to pull the 2 out front. Okay, equals 1 to 1,000. Okay, plus k equals 1 to 1,003. Okay, that produces a sequence, and that produces a sequence. So what I did is I pulled the 2 out front, leaving the k right here. And then I'm going to add these 3's up separately right here. Aren't there going to be 1,000 3's in this list? Does that make sense? Okay, let's do the easy one first. If it's just a 3 every single time, how many of them are there? There are 1,000 of them. So this is going to be 1,000 times 3. That's the answer to this one. That's an easy one. This is going to be 2 times some answer right here. Now take a good look at this. Didn't we figure this out already? And more importantly, don't think, well, that's 500,500. Think it's going to be 1,000 times 1,001 divided by 2. And then let's do the arithmetic. Cancel here and here. This is going to be, let's see. Yeah, we're going to get 1,000,000. Yeah. That's what it is. Plus 3,000. So altogether, let's see, 1,000,000 plus 3,000 is 1,004,000. Okay, now I want you to stop and think about this for just a second. We just added up 1,000 digits, 1,000 numbers, and we did it this quickly, and we were yakking about it the whole time. Okay? So, on Monday, you need to come with 9-1 done, or you come and see me sometime before class so we can get straightened out what your questions are. Okay? Because on Monday we're going to do 9-2.